laws of physics are the same for all inertial frames. His second postulate states that the speed of light is the same for all observers. He simply assumes the phenomenon that Lorentz has been struggling to explain. From these two postulates alone, Einstein deduces exactly the same equations Lorentz discovered earlier. But now they have a very different meaning. The fundamental concepts of space and time have become intertwined. The essence of the idea can be understood by visualizing time as if it were another dimension. Albert, standing still in space, flows through time, so that a vertical line represents a fixed point, x equals 0, in his reference frame at different times, while a horizontal cross-section represents simultaneous times in different places. On the other hand, someone in motion, Galileo for example, traces an oblique path. So while what Albert thinks of as a fixed point makes a vertical line, Galileo's idea of nothing happening appears as a tilted line at x prime equals 0, or anywhere else in his frame. But of course, if Galileo had drawn the picture, his line for standing still would be vertical, and Albert's would be tilted backward. The same idea can be used to show the relativity of time. When Henry and Albert observed the same expanding light sphere, it reaches their detectors at definite points in time and space. These are called events. Meanwhile, the light itself traces out a cone. To Albert, events on the horizontal cross-section are simultaneous. For him, one of Henry's detectors flashes first. Then both of his own flash simultaneously. And finally, Henry's other detector flashes. So he thinks these two events are simultaneous. But Henry thinks these two events are simultaneous. So not only are Henry's lines of constant position tilted, but so are his lines of simultaneous time. For Henry, simultaneous events take place everywhere on a tilted cross-section. So he thinks one of Albert's signals goes first, then both of his, then Albert's other signal. Of course, if Henry were drawing the picture, he would draw his lines of constant place and constant time perpendicular to each other. Amazingly, that wouldn't change the light cone at all. This way of looking at things is called a space-time diagram, and many of the strange effects of relativity can be visualized this way. For example, Albert thinks that Henry's ruler isn't quite a meter long, while Henry, seeing Albert speed by, thinks Albert's ruler is shorter. On the space-time diagram, Albert measures lengths on his space axis, where Henry's ruler is shorter. But on Henry's axis, the situation is reversed, and Albert's ruler is shorter. And what about the mystery of the clocks? How can each think the other's clock is slow? On the space-time diagram, just follow the bouncing light beams. On Albert's time axis, Henry's ticks are farther apart than his own. But on Henry's time axis, Albert's ticks are farther apart, no matter how he looks at it.